So here we are on session 2 after last week's whirlwind. Sorry about having to cover such an extraordinary amount of material in an hour plus, but now we'll get into the more focused discussions of our own period. And the second session, which I've called Astronomy, Ptolemy to Galileo. And the reason I begin with this one is astronomy became the device for all of the sciences to peek their way into, or poke their way into, I should say, the popular consciousness. This became the way in for all students of science. It opened a plethora of questions which led to physics and the solutions provided by physics and advances in mathematics and the like. So we're going to begin here. And we're going to first talk about the Ptolemaic universe, the set theory that dominated the ancient world all the way through the Middle Ages, all the way into the 16th century, certainly, before it was realistically questioned, even though there were people in the ancient world who suspected that this was not the case. But Claudius Ptolemy, a Hellenized Greek, so in the ancient period that would have been the early empire of the Roman world, between 100 and 170 is their guess. He's a Roman citizen, he's based in Alexandria, and remember, the hotbed of intellectual life in the Mediterranean during the Roman world was the Eastern Mediterranean, and particularly northern Egypt. And Alexandria was one of the real centers of intellectual life. He was a mathematician, he's an astronomer, he's an astrologer, a geographer. His large work, the Almagest, it's written in Greek. It's his key work. It was copied by everybody through the ancient period. It's annotated by every culture that gets their hands on it, and it was accepted as authoritative by Byzantine, Arabic, and Christian commentators. So it became quite the sensation in the Arabic world as well. And of course, would then get translated into Latin during that great translation movement that we referred to last week in the 12th century in Spain. So Ptolemy represented the culmination of a long tradition that had stretched from the Babylonian period in Western Asia and in Egypt and in Greece proper, traditions that did very careful celestial observations and mathematical calculations that plotted the relationships of the movements of stars in the greater heavens, as they would have thought of it. His greatest predecessor was a Greek astronomer and mathematician in the period before the Common Era, a couple centuries earlier, Hipparchus of Nicaea. Hipparchus was among other things, the inventor of trigonometry, which helped his calculations of what should appear where in the heavens. And he's the first to accurately calculate the motion of the sun and the moon. The standard Latin edition of the Almagest of Ptolemy was translated from the Arabic, as I referred to a bit ago, by Gerard of Cremona, one of the greatest of the medieval translators at Toledo in the late 12th century. It's a geocentric model, meaning it has the sun at the center. It assumed spherical universe, a spherical cosmos, with an unmoving spherical Earth at the center of it. And if you look at that image in the lower center, these were thought of as crystalline shells. It was almost like one of those Matryoshka Russian dolls of a shell within a shell within a shell within a shell. And it was thought that the stars, planets, celestial bodies, depending which layer you were looking at, were sort of embedded in the shell. And it assumed, because Aristotle made a big deal of it, that the perfect shape was the circle, and kind of ideal shape, that the movements had to be circular. And that image of the shells at the bottom indicates the order of position of each of the shells: Moon closest in, Mercury, Venus, Sun, Mars, Jupiter, working one's way out to the fixed stars. And here, as late as the early 16th century, on the lower right, we see Peter Appian's Cosmographia, an image from one of his woodcuts of the entire universe, which of course was always depicted as a series of circles. And when you ever would see astrological charts, they always radiated out in circular directions. So this was the commonly accepted version of the universe as it came from antiquity, and blessed by the philosopher himself, Aristotle, as he was known to the Arabs and to the Greeks. And now, for a couple of sessions, you'll permit me the indulgence of animated GIFs to illustrate what we're talking about here. Now, there are problems with the geocentric cosmos, as a number of people are going to point out when we get to our period. And the greatest of the problems is that several of the moving bodies have retrograde motion. And I'm going to use in the image on the lower left, actually in both images, I'm going to use Mars as an example of what this means. So in verbal description first, before we look at the images, in general, Mars appears to move a little eastward each night in relation to the fixed stars. About every 2 years, for a few months, Mars seems to change direction and move westward. So what we're seeing, in effect, if we look at the big blue image, this image is showing, if you look at the bottom of it, what you see is what is actually going on in our conception of the universe. So you have the blue Earth, the red Mars, the stellar background, sun in the middle. You see Earth's orbit. And as it moves, as Earth moves and as Mars moves along their respective orbits, you see how Mars follows an S curve up at the top of the image. In other words, there's times when it seems to be moving from the right to the left, but then there is this time right there, if you look at that movement, it looks like it moves in the reverse direction. And this had to be explained. What are we to make of this? I mean, we know why it looks like it's moving in an opposite direction from its established direction, because we know what the actual orbits are. You'll see it again in that tall image on the right of the screen. So the E is Earth, the M is Mars, the S in the middle of the sun. You see how at a certain point in our tighter circle, the Earth, if you will, on a right to left scale, passes Mars, which means that Mars looks like it's going backwards again. And this totally perplexed Ptolemy and some of the ancients, and it needed to be addressed. So planetary, looking at that second bullet up higher end on the slide, planetary orbits are not in the same plane as Earth. The so-called our orbit is referred to as the ecliptic. The orbit pattern takes on an unexpected irregularity that conflicts with Aristotle's assumption of perfect circularity. So what is to be done? So what is to be done is the invention by Ptolemy of epicycles. And his solution was to posit an epicycle, which is a circular orbit of each planet that itself orbits around the Earth. So if you look up at the top diagram, there's the Earth and there's a planet. And essentially, it isn't the planet going around the Earth, it's the epicycle of the planet, that gray shaded blob. The planet itself is going around in this epicycle direction, and then that whole traveling ball, if you will, is going to follow the deferent, which is the circle around the Earth. And so it's going to have this kind of loopy action. And if you look at the middle image, the moving GIF, you see an epicycle moving around, and that projection at the top of the line is what it looks like from Earth. So as a planet moves around its epicycle, the center of the epicycle, called the deferent, moves around the Earth. When its motion brings it inside the deferent circle, so when it's at the bottom of that circle, it seems to be reversing direction. It undergoes what they refer to as retrograde or backward motion. So Ptolemy added refinements, which he regarded as a mathematical device, an explanatory device to account for the measured differences. You know, and there's a difference. I'll use this phrase, device. At this period, in the 16th and 17th centuries, the great respected science was physics. How does the world actually work? Astronomy, with its mathematical computations to explain certain motions, was seen as inferior. It was seen as sort of a parlor trick, a card trick that you used to explain reality, that it itself wasn't a valid representation of reality. And indeed, there's reason to believe that Ptolemy did not actually think that epicycles existed physically, but that they were an explanatory device to explain this kind of boogie-woogie motion that planets had in their movement around, their alleged movement around the Earth, which isn't really what they're doing. So it's hard to explain something that doesn't exist. Anyhow, Ptolemy added these refinements to account for the measured differences in the angular speed, which is the rotation rate of planets. The rotation rate of planets seems to change relative to Earth at different points of nearness and farness in their orbits, and he needed to explain how this was going on. So the epicycle was conceived to move at a constant angular speed with respect to a calculated spot in the greater deferent called the equant. So to account for these changes in speed, he had to hypothesize that there's this other point in the circle that the planet is the deferent circle, the planet is following around the Earth, and that it's only, the speed is constant only in regard to that point, the equant. So it's this, he has to postulate this non-existent point, this vanishing point, to explain how the motion could be regarded as constant from some referent point in the universe. And the epicycle center would appear to move at a steady angular speed from that point. The equant is placed so that it is directly opposite to Earth from the deferent center, known as the eccentric. So the Earth is off center. Here's the eccentric, that little plus sign there. Earth is left of the center, the equant is right of the center, and you needed to postulate all these respective points to maintain the hypothesis of circularity, which is a lot of work to go through to explain what should be a simple explanation from observation. these extraordinary, as I say at the bottom paragraph there, these extraordinary convolutions were necessary to maintain the assumptions of classical philosophers, aka Aristotle, about celestial motion being perfectly circular. If you were to give it up, you could come up with a simpler explanation, which is what is going to happen. There was a man, Aristarchus of Samos, very early on, who proposed a sun-centric, a heliocentric universe. But the theory was overwhelmed by the growing prestige of Aristotle during that Hellenistic period. So Aristotle's heyday is in the 340s and 330s before the Common Era. And here's a man born after the death of Aristotle who proposes the sun at the center in the very period when Aristotle's theories are gaining incredible traction in the schools of philosophy in the Eastern Mediterranean. And so he is, although his theory's out there, nobody really knows about it. It gets walked over, it gets disregarded. And a lot of things along the way in the ancient world happened this way because of the prestige of both Plato and Aristotle, which we talked a bit about last week. Then along comes Nicholas Copernicus before our period. And our period's going to be about validating his intuitive observation. You see, he's born in 1473, about the same time that Leonardo da Vinci's born, about the same time that Martin Luther is. He's a little before, I think Luther's born in the 1480s, and he lives to 1543. So he makes it to almost to the midpoint of the 16th century. And he's quite a Renaissance figure. He is the Renaissance man. He is a polymath of the highest order. He's Polish. In fact, this painting is from a fresco in the town hall of Torun, which is his hometown, wherever that is in Poland. He is a mathematician. He's an astronomer. He's a doctor, a physician. He's a cleric, I believe. I don't know that he's actually a priest. He might have been ordained a deacon. He's a canon lawyer, a church lawyer. He's a diplomat. He's a linguist and translator. We know, among others, that he was fairly fluent in Polish, German, Latin, Greek, Italian, and Hebrew. And who knows? Probably, if he knew Polish, he may have known bits of other Slavic languages that were being formed around the same period. So he comes of age in the period of early printing, the so-called period of the incunabula. Incunabula are books that were printed after Gutenberg invented the printing press in the 1450s, but before 1500. And I don't quite remember why they call them incunabula, but everything that was printed in that period is so referred to. He had access to Arabic texts on astronomy and astrology, as well as those of contemporaries like the great fellow polymath and Renaissance genius, Giovanni Pico della Mirandola, who died in 1493 as a young man who would have only been about 10 years older than Copernicus, even though Pico dies when he's about 30 or 35 years old, somewhere around there. Anyhow, there are questions. Since Copernicus never publicly mentioned heliocentrism until 1514, so by that time he's about 40 years old or so, there is much speculation about his motive to do so. There had been no radical breakthroughs in observations. There are no telescopes. There are no extraordinary mathematical theories positing, more than positing, but adding heft to the arguments that the sun is the center of our solar system. And so why then? He was Clearly dissatisfied with Ptolemy's equant and other irregularities, some have suggested that he intuited Earth's motion because of its similarity to other spherical bodies. Who knows? But this is, when you're a genius, these things happen, I suppose. The following quote is from a 1514 summary that he did not publish widely, although we get our hands on it because it came down to us intact, the so-called Commentariolus, the little commentary. And this was circulated only like Samanstat in the Soviet Union, only among the underground of his friends. And in it, he details his objections and some of his ideas. Quote, yet the widespread planetary theories advanced by Ptolemy and most other astronomers, although consistent with the numerical data, you can trump up a mathematics that makes it seem consistent, seemed likewise to present no small difficulty. For these theories were not adequate unless they also conceive certain equalizing circles, or epicycles, which made the planet appear to move at all times with uniform velocity, neither on its deferent sphere nor about its own epicycle center. Therefore, having become aware of these defects, I often considered whether there could perhaps be found a more reasonable arrangement of circles from which every apparent irregularity could be derived, while everything in itself would move uniformly as is required by the rule of perfect motion. So he says, maybe there's another way to conceive of this. And he comes up with heliocentrism, sensitive to the outcry that this is going to generate. He did not live to see the final printing of the masterwork, the De Revolutionibus Orbium Celestium, concerning the revolutions of the orbiting stars or bodies, until, as legend has it, the actual day he died. There actually is a legend that on the day he died, the book got published. There are 7 postulates stated in the Commentariolus, the earlier book. 1, there is no one center of all the celestial orbs or spheres. There is no one center. 2, the center of the Earth is the center not of the universe, but only of gravity and of the lunar sphere, the moon. 3, all the spheres, planets, encircle the sun, which is, as it were, in the middle of them all, so that the center of the universe is near the sun. 4, the distance between the Earth and the sun is imperceptible in comparison with the loftiness of the firmament. In other words, he knew that the stars were way, way, way out there as compared to the distance between the Earth and the sun. 5, whatever motion appears in the firmament is due not to it, but to the Earth. It's not the firmament that's moving, it's Earth that is moving in relation to everything else that is moving. Accordingly, the Earth, together with the circumjacent elements, those that are adjoining it, perform a complete rotation on its fixed poles in a daily motion, while the firmament and the highest heaven abide unchanged. So, in effect, we're doing, relatively speaking, they're so far away, we don't see big changes in their movement. We see more dramatic changes on our closer in range. 6, what appeared to us as motions of the sun are due not to its motion, but to the motion of the Earth and our sphere, with which we revolve about the sun as any other planet. The Earth has then more than one motion. So it's revolving and rotating. 7, what appears in the planets as retrograde and direct motion is due not to their motion, but to the Earth's. It's because we see them as we're moving along a different orbit, so that relative one orbit to the other orbit, it looks like they have changed their motion and are moving backwards. The retrograde motion that we spoke of earlier. The motion of the Earth alone, therefore, suffices to explain so many apparent irregularities of the heaven. And from his later publication, the De Revolutionibus, there's this image of Earth, the sun at the center, and Earth and everything else revolving around it. Now, how did people respond to this? He dies in the 1540s. Well, this is still the heyday of the Reformation and the Counter-Reformation. So you have Christianity not only in turmoil, not only on the verge, more than on the verge, engaged in wars of both words and weapons in places, and you are in the active lifetime of Martin Luther and John Calvin, the great Protestant theologians of the 16th century, and the Council of Trent is about to begin in 1545, the great response of the Roman Church to Luther and Calvin. So 16th century reactions were muted. We don't get a lot of reaction. Luther and Calvin objected to the system's apparent contradiction of Scripture, but Protestant universities had no problem, up in Germany, had no problem regarding it as a useful predictive mathematical tool, not as a cosmological reality. So they could divorce, it was still in this realm of mathematics. You could explain the motion, Occam's razor, you could explain the motion of the planets using a simpler geometric and mathematical model than the earlier one of Ptolemy, but it was still not to suggest that this was the real universe, the cosmological reality. In Catholic circles, there was a Dominican theologian who was also an astronomer, Giovanni Maria Tolosani, who objected on philosophical grounds, not just on biblical grounds. He's an Aristotelian, he's a follower of St. Thomas of Aquinas. And he's arguing that the motion of the Earth was an unproven, it's only a mathematical assumption. It's not a real actual proof. And Aquinas considered math, as we pointed out earlier, as an abstract methodology inferior to physics, which deals with the real world. And in Thomas's terms, the use of mathematical models could not explain physical causes. If you're going to explain how the Earth is moving, you have to do it through physics, according to Tolosani, not through just mathematics. There's still this sense of a divide between math and the other sciences. The Council of Trent never mentioned Copernicus or heliocentrism, and they meet for 30 years, from 1545 to 1575. Tolosani goes largely ignored, and church objections don't really get serious until we get to Galileo, which we'll be talking about in a little bit. So what wasn't understood, and that note in the box in the middle, is that heliocentrism would result in the rethinking of all of physics would have to be rethought as a result of changing the model, the astronomical model that people were working with. Because as we will see, leading up to Newton, people first had to explain what the orbits looked like, and then had to begin explaining why those orbits should be there working the way they do. Because it wasn't following circular motion, as we will see, and people needed reasons to understand why things were allegedly so off kilter. One of the early astronomers that just barely gets into the 17th century, Tycho Brahe, who's Danish, and he's an astrologer as well as an astronomer, and he's an alchemist. They all went together in that period, as you recall. And he's a doctor. And again, all the sciences, if you dabbled in one, chances were that you were going to be dabbling in them all. It's the pre-telescope era, but Brahe makes spectacular, detailed observations using instruments that he's created, he starts measuring the arc movements of things to within a minute, within a 60th of a degree. Full circle is 360 degrees, so an arc minute is 1/60th or 1/3600th, I suppose, of the whole circle. And he starts making observations and building tables that really plot close measurements so that when the people who come prepared with better models can use his tables to make their case, as we will say. He did not fully accept the Copernican model. In fact, he created a hybrid theory that merged geocentric and heliocentric details. So if you look at this blue circle at the bottom, so he has the moon and sun revolving around the Earth, but the other planets revolve around the sun. So it's this kind of crazy thing going on here. Anyhow, he thought he could explain the universe through this alternate model. Now, he made great strides in developing tools that he used in his observatory in Denmark at Uraniborg Observatory. And you see, there are dozens of these measuring instruments. In fact, if you look at this picture from 1580 in the upper right, this is actually like a mosaic that was set in the wall of the observatory. And in each of these little windows, there's another, this is Brahe, and there are all these instruments that he created. And I've put closer views of a couple of them. This is the armillary, which is used to measure altitudes and azimuths. And indeed, if you look at this image in the upper left, and it's showing you how from a center point on Earth, you can measure altitude. This is what's being measured. You're pointing at a star and you want to see the height of it as an angle, and the azimuth is from a point due north. And these instruments were going to become quite central to navigational instruments used in sailing, which is the technology. It's the market. World trade, and I've got a couple of slides that talk about this, right, following in a minute. World trade became the market that demanded technological breakthrough. When you look back at the history of technological development, often things like the theory for the steam engine, for instance, was in place for centuries before someone invented a useful steam engine. And the reason was there wasn't a market up until that point that required the application of theory to a significant breakthrough. So what we find in the 17th century is that the exploitation of world markets through navigation forced the invention of a number of things, not just physical technology that helped sailing by being able to plot position at sea against the stars and planets, etc., but inventions of banking conventions, inventions of trust companies. But I'm going to talk about this in a little bit when we get to another slide. Down here, this is the so-called bipartite arc to measure angular distance. So altitude is the angle of a celestial object measured upwards from the observer's horizon. Azimuth is the angle formed between a reference direction, for example, north, and a line from the observer to a point of interest projected on the same plane as the reference direction, orthogonal to the zenith. So in other words, so if you pick a north and you know where north is because you have a compass, it's going to help you measure the azimuth, so the distance following, in effect, following the circle of the Earth to the other object that you want to find the distance from. And angular distance is the angle between two sight lines, as is depicted below. And all of a sudden, all of this stuff, because of sailing and the explosion in sailing technology, is needed. And along comes a very practically minded man who is an astronomer and who has a taste for technology, and they start making these things in the age of imperial expansion. So I talk about economic development and technology a little bit on this slide. So navigation is the great driver of technological development in the 17th century, and it was because of the expansion of trade and the exploitation of foreign markets in Asia, Africa, and the Americas. Here, a painting from 1622, Hendrik Vroom's view of Hoorn, a harbor, bunch of Dutch sailing ships. Latitude was fairly easily computable, even in this period. And ever since the ancient world, the calculation of latitude was substantially accurate. The navigator used a sextant or an astrolabe. And here we have an image of one, in effect, to measure the angle that the North Star, Polaris, sits above the horizon. And then you use some well-known trigonometry to do the calculation. And that works because no matter where you are moving north and south along latitudinal line, each of these horizontal lines is a latitudinal line, no matter where you move, the North Star is stably referenceable to no matter where you are. So then you just use some trig and you can figure out whether you're way down here in Central America or you're up here in Florida or you're up here in Canada. And they knew how to do that. The problem was longitude. And this is one of the great, if they gave out Nobel Prizes in this period, this would have been the source of, somebody would have announced a prize for, and that they did announce prizes for being able to calculate longitude. The problem is there's no reference North Star as you go east and west. But if the navigator knew the local time where he was or she was, and the time at Greenwich or some other reference point like Greenwich, then longitude could be calculated. Now, the only way you could do that would be by having a clock that could overcome the ship's motion. And the contemporary pendulum clocks were just useless in that regard. So you find later in this century, there are a number of clocks developed, especially by the Dutch, who were the great navigating breakthrough scientists in this period, but especially by the Dutch. But it wasn't really until the 1730s that a sufficient clock was developed that could do these calculations. By 1673, the great Christian Huygens had invented a clock with a balance wheel and a spiral string for regulation. And this became the model for the later marine chronometer as it was developed in the early 18th century. And by that same token, for modern wristwatches, the spring technology. So solving the problem of longitude with accuracy became, they could ballpark it a bit, but to develop it with real accuracy so you knew exactly, you could calculate exactly where you were, instead of let's just keep heading west until we hit Brazil. was the issue. And buttressing that point, and I very deliberately selected the Dutch to talk about in this period. I should mention, I don't have a slide that depicts it, but yes, the voyages of discovery in the previous century were carried on by the Dutch, but also by the Portuguese, the Spanish, who set up colonies, and the English, who set up colonies. In other words, in the medieval period, Italy and its great maritime cities like Venice and Genoa had dominated European trade, sea trade. But with the voyages of discovery, it was all the countries on the Atlantic that came to the fore, and the centers of world trade, European-based world trade became those four on the coast: Spain, Portugal, Holland, and England. Spain was largely interested in finding sources of mineral wealth that they could import from, particularly from the Americas, as we all know, the silver mines in Latin America and gold mines from Cortez onwards was their essential focus. But the two countries focused on trade and who had more mature market economies at the time were Holland, the Republic of Holland, I should add, and England. And both of whom had, by this point, stable parliamentary governments that favored business classes and the building of stock companies, rather than, as in Portugal and Spain, the endowment by a monarchy of monarchical sponsored companies that weren't nearly as keen on building up the sorts of trade that the emerging bourgeoisie of England and Holland were interested in building. By the time we get to the mid-17th century, England is not keeping up with Holland in this expansion for two big reasons. One is that they are in the middle of a civil war between 1640 and 1660, which totally disrupts the development of a stable market. And the second one is the smallpox plague outbreak of the 1660s, just demolishes what's left of the economy. So this becomes a fait accompli. The Dutch Golden Age, this little place, becomes this powerhouse of world trade. And early in the century, there was the founding of, I don't know how to pronounce Dutch. If it were vaguely like German, this would be Verenigde Oost-Indische Company, or the famous VOC, which is the United East India Company, also called the Dutch East India Company. This was an organization that in effect created the Amsterdam stock market. I have a painting over here of the old exchange of Amsterdam, the first world stock market, because it's a stock company, and it's a stock company that it's got like its own, not only does it have its own ships, it's got like its own army. There are uniforms, military uniforms issued to people who man many of the ships and the like, and a great many contributions to science, math, and technology in this period were by Dutchmen because they needed And I included a picture down here. This is a replica of one of the VOC ships, the Deifkin. They are, if you remember your American history from the period, they are in New Amsterdam. They are in, let's expand this Dutch trade route map. They are on the west coast of Australia, which at the time was known as New Holland. They are importing, they dominate the area in the Indian Ocean north of Australia. They have established the so-called spice routes. They're bringing spices and silks and porcelains and luxury goods from Japan. They're bringing cloves and cinnamon. It's because of the company that the tulip mania develops in the middle part of the century. They are importing sugar from Dutch Brazil in this period. The part of Brazil that they control. They are controlling timber importation from Scandinavia. They are all over the map, this little country. They have invented things like the stock company, probably contemporaneously with the British doing the same thing. The British are going to make a great contribution by the end of the century, though. They're going to legally introduce the principle of limited liability, LLC, and if you will, the limited liability corporation, which defers exposure away from individual investors. Okay, you can put your money in, you can buy shares in the East India Company, or in particular ships, as they often represented. In England, you could buy the 16th, they weren't using the decimal system, you could buy the 16th of a ship. But if it did some great damage, or if it lost some great property, you were only liable to the extent of your own contribution, your own investment. You can lose your investment, but they couldn't come after your other stuff. And so this made investing, in one sense, risk-free, which was a huge advancement and was, if you will, a banking technology breakthrough. Here is a depiction of that old exchange in Amsterdam. We have a number, you can think of the Rembrandt and Frans Hals portraits. We looked at a lot of them closely in the Reformation and Counter-Reformation class, and it's off our agenda here, but you could see these characters fitting right into those portraits of substantial burghers in Amsterdam and Rotterdam in this period. So this is the market that said, give us technology, give us astronomical breakthrough, give us better calculations for steering ourselves around the planet. So on to more technology. The refracting telescope gets invented, and it is called the Dutch telescope. Why are we not surprised? Holland was the center for the study of optics. Even the great Dutch Jewish theologian and philosopher Baruch Spinoza was a lens grinder, was a man creating optical lenses. And Holland, Amsterdam, Rotterdam, these were centers of lens grinding. Although the historical inventors disputed, the first popularized telescope is credited to Hans Lippershey in 1608, and it causes a sensation. Its magnification was 3 times. So it would be a cheesy pair of kids' binoculars now, but it was a sensation. And word gets everywhere. And as we will see in a forthcoming slide, and it gets to word gets to Galileo in Venice the next year, in 1609. He goes, what is this slice of madness? And he takes it to the next level. So a basic refracting telescope has two optical elements, a so-called objective, one lens on one end, and an eyepiece lens. The objective is a large lens that collects light from a distant object and creates an image in the focal plane. The eyepiece is a sophisticated magnifying glass through which you look at that image. So the basic design of these early refracting telescopes consists of a convex objective lens and a concave eyepiece. So here is a model of an earlier guy. And here's a little explanation of refraction down here. Since a lens is denser than air, it slows down light waves as they enter. As each wave front meets the curved surface of the lens, some parts slow down first, causing the light to bend or refract. And so here is what's going on with light waves as they come through the glass, and as the comes through the glass and the light gets refracted to a focal point. Okay. Galileo, as I mentioned, sees the telescope in Venice in 1609. And within weeks, he's produced an early design that has improved on the one he was shown. He soon made an instrument with a large objective lens that produced 23 times magnification. Okay, now we're getting serious. It was the first to be christened telescope at a banquet in Venice. Somebody made a speech and made up this neologism, this made-up word, telescope, being able to scope from afar. The Galilean telescope has a converging objective lens and a diverging eyepiece lens. The eyepiece is situated in front of the focal point of the objective at a distance from the focal point equal to the focal length of the eyepiece. That's a mouthful. And I don't want to spend too much time trying to look at the physics of it, but this is sort of what the thing looks like. Here's the eyepiece lens, here's the objective lens, and the image comes through as straight up, and then it's magnified through the eyepiece. Kepler, Johannes Kepler, a German in the period, in 1611, he steps up the game. He's developed a model using a converging eyepiece that expands the field of vision so that you could look at you get not just magnification, but a wider view of what you were looking at. The objective forms a smaller upside down image. The eyepiece functions as a magnifier of that image. So this gives you magnification and across a wider swath. There's a problem that develops though in early telescopy called chromatic aberration. And this is particularly found in Kepler's telescopes. It's a distortion caused by the fact that different colors have different focal points. And the only way you can sort of, so different colors come in, but they're not all focusing at the same point. They're focusing at different points. So how do you minimize the fact that red is focusing over here and blue is focusing over there? How do you get around that? Well, one of the ways you get around it is by increasing the focal length of the objective lens. And so people got ridiculous with this. By 1672, a man named Johannes Hevelius, I forgot what nationality he is, he might be Swiss, had constructed a telescope with a focal length of 148 feet. You had to build scaffolding around it. And here's a woodcut of what this thing looked like. So this thing was so unwieldy that, I mean, I don't think anybody was really using these things, but it managed to correct for some of the chromatic aberrations. And until we get to reflecting telescopes and away from refracting ones, this is going to be a problem. But that's something I believe I'm talking about next week when we get to Newton. Anyhow, Kepler. So now we're again entering into the heartland of the 17th century. He's a mathematician, he's an astronomer, he's an astrologer, sounds like all the other guys. He lives up until 1630. He's an assistant to Tycho Brahe. So he publishes De Stella Nova concerning the new star in 1605. He publishes a book about the appearance of a new star, Kepler's supernova, SN 1604, which called into question Aristotle's doctrine that the celestial sphere was perfect and unchanging. He sees a supernova. Something has happened. It's changed in that outer crust layer. Something's rotten in the Aristotelian playbook. In another work, the Mysterium Cosmographicum, it's an early work, he suggests that planetary orbits could best be geometrically represented in a heliocentric model. He even included a chapter reconciling heliocentrism with biblical geocentric passages. So he knows by the 1620s, the various religious powers that be are going to come after him. And he's already trying to rationalize, as Galileo tried, how this could be consistent with biblical sources. Then in Astronomia Nova, a book from 1609, provided one of the seminal turning points in astronomy, having at his disposal a mass of data on planetary motion, including much of it that had been collected by Brahe, the guy he was an assistant to. Kepler was able to synthesize the first two of his three laws. So now we get the early understanding that these things are not moving in circles. And we get this because he's got tables of carefully accurately calculated movements from Brahe that he and the other guys using the early telescopes are able to establish as correct. And he develops first the law of ellipses. The path of the planets around the sun is elliptical in shape, with the center of the sun being located at one focal point, okay? There is another focal point symmetrically opposite the sun at every point in the orbit. The sum of the distances to each focal point is constant. So there are these ellipses. Can't explain the ellipses, he says, but they're there. Newtonian gravity later on will explain the physics of elliptical orbits and changes in the planet's velocity. Right now, he can just note that this is the case. He says, I got to tell you, every one of these moving things we look at, they follow an ellipse with two different focal points, okay? Then he develops, I know, don't you love the cute animations? This second law, which is the law of equal areas. If an imaginary line drawn from the center of the sun to the center of the planet that is sweeping around will sweep out equal areas in equal increments of time. So if you look at this upper image with the areas that are blue and gray, the area of each of these color slices, of each of these pie slices, the area is the same, okay? So when they develop the math to really measure this accurately, it'll prove out to be the case. and Newton is going to make great hay out of this. The Epitome Astronomiae Copernicanae and the Harmonices Mundi. In the period between 1618 and 1621, he publishes two books that summarize his heliocentric positions and introduce his theory of harmonies and congruence in nature, particularly in planetary motion. And these he introduced his third law, the law of harmonies. The ratio of the squares, by the way, I should mention, as early as the Pythagoreans in the ancient world, say the 5th and 6th centuries BC or BCE, they had argued, the Pythagoreans, that if you looked at the ratios of movement of moving celestial bodies, they are at intervals that suggest the intervals in musical key relationships. And they thought that, and they invented the phrase that if you could hear the movement of the stars, it would be the so-called music of the spheres, that there were ratios that were harmonic ratios. So here Kepler creates the law of harmonies. The ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. So here's the sun, and the squares of the time it takes to get around the sun for each of these planets would be equal to the cubes of their average distances from the sun. So he's beginning to get the math right about the movement of the planets. This would eventually provide the foundation for Newton and others to theorize that the gravitational attraction between the sun and its planets decreased with the square of the distance between them. Let me kill this phone in the background. Okay, sorry about that. Optics, telescopes, physics, and math. Kepler's work is polymathic. He laid the basis of modern optics. He designed telescopes of greater magnification. He introduced the orbital model of planetary motion, theorized a hypothetical atomistic basis of symmetry. He expanded the field of geometry, and he laid the foundation for infinitesimals and approximations in math. Why do I introduce this last line? Calculating a lot of motion, a lot of moving objects, which we now know is the mathematics of calculus, the branch called calculus, differentials. In calculating it, there are, because really when you're doing calculus, you're doing very advanced and accurate approximations, because many things approach limits like zero without ever getting there, as you see something moving in relation to something else. And a lot of the future of math in the 17th century is going to be, and we're going to talk about this next week when we look at Newton and calculus, but the calculation of infinitely small differences as they approach zero, for instance. It's like trying to measure the area under a curve. As you try to do it, as the curve gets smaller and closer to the x-axis, closer and closer and closer and closer, you're dealing with the calculation of infinitesimals, and it becomes a big issue, and you need a separate branch of mathematics to be able to do it. So empirical observation and precise measurement have now replaced scholastic deduction from first principles. The focus, and this is the thing I was trying to stress last week, the focus has now changed from why to a concrete how. People are tinkering with engines. I mean, you look at these diagrams, these moving GIFs on the page, and all of a sudden it's like, practical calculations. I'm inside the engine of a 62 Chevrolet here, right? It's the question becomes a mathematical and engineering set of questions and less the ultimate meaning of it all, which was sort of the medieval obsession. And if you can talk about the change in a climate of opinion, when you're within one climate of opinion, a single one, by which I mean when you're in an age which has defined its questions a certain way, somebody asserts A, and somebody comes along and asserts non-A, and then you argue back and forth, is it A or is it non-A? When a climate of opinion has changed, when other concerns have moved in to change the focus of attention, somebody in the earlier world has said A, and now somebody in the new world, they don't say non-A. They just move on to a different question. They don't recognize the language or the concerns of the earlier frame of reference. It's not a relevant point. How many angels are there on the head of a pin? Well, I've never thought of that because I don't care. But it was of dialectical concern in the 11th century. Do angels have spatial extension? Anyhow, you get the idea. We're now in a new world. So the full assault on Ptolemy has begun. And we come to the breakthrough of the great Galileo di Vincenzo Bonaiuti de Galilei, 1564 to 1642. Again, you notice that the lifespans of these guys are overlapping very directly. They're all peers. A lot of these guys knew one another. Galileo is called all sorts of things: the father of observational astronomy, the father of modern physics, the father of the scientific method, the father of modern science. He takes his heliocentrism very rigorously. In 1610, he publishes Sidereus Nuntius, the celestial messenger, if you will, with the results of his telescopic observations of the moon, and concluded that the surface was not a perfect sphere. The moon isn't this shiny 8-ball up there in the sky, but it is this ragged looking ball marked by craters and mountains, and it is a rock. And he makes sketches. These are one of the sketches from the book. More importantly, his discovery of 4 large satellites orbiting Jupiter caused a sensation because, one, it exploded the theory that all celestial objects revolved around the Earth, because here are things revolving around Jupiter. And 2, by proving that they were substantial, meaning these are rocks. These are not some kind of ethereal orbs in the out there. We are now, what is here up close and what is out there at a distance are substantially the same kind of thing. So a final nail in the coffin of Ptolemy's geocentrism was his observation of the full phases of Venus as it orbited the sun, which would not be possible if the sun was in the fixed shell of stars in Ptolemy's theory. And you see that down here. In other words, here from the Earth, he managed to observationally see that Venus going around the sun went through all phases, like the phases of the moon, where it's got a light side and a dark side. And he could see this happening to Venus as it went around the sun. So that could not have been the case if the sun was another object bound in the firmament the way the Venus allegedly was, all revolving around the Earth. There's great resistance by the church. Remember, he's in Italy, and the Inquisition, you are still in the fallout of the Protestant Reformation. You're in the 1630s. This is the Baroque period. This is the period of the great assertion by the Roman Church of its power and authority. Think of the great Baroque churches that are constructed all over the world in this period. And so this is the militant church in full strength. And at the same time, this is the period from 1618 to 1648 of the 30 Years' War in Germany, where Protestant countries of different brands of Protestantism and Catholic countries are all lining up either for or against the Habsburg monarchy in the Austro-Hungarian Empire, and all the splinter countries of Germany are making their allegiance one way or another, and world Catholicism and world Protestantism are at each other's throats. So this is not a world in which Galileo is going to be taken quietly. He is now it is more of a challenge to the church and the Protestant churches, as well as the Catholic Church, as it was in the age of Copernicus. So there were still technical objections to Galileo's heliocentrism based on theories that combine the two systems, like Tycho Brahe's, and Galileo responded to these in multiple publications. But it's really when in 1616 the Roman Inquisition declared heliocentrism to be foolish and absurd in philosophy, I'm quoting from their final diktat, and formally heretical, since it explicitly contradicts in many places the sense of the Holy Scripture. So after several attempts to defend his theory, he's finally placed under house arrest in 1633. The Inquisition wasn't this full tilt, especially the Italian Inquisition. It was nothing like the Spanish Inquisition and the Crusades against the Moors and Jews at other periods. The Italian Inquisition was more of an intellectual. I mean, he's put under house arrest, ultimately. There's a picture in Venice of a Last Supper. I showed this in one of the classes by Paolo Veronese. And in the Last Supper, he makes it look like the wedding feast of a German noble family, and they're clowns and they're acrobats, and the Inquisition was scandalized. So they hauled Paolo Veronese in, and they said, "You can't do this. You know, this isn't a Last Supper." So he changed the name of the painting. Said, "Okay, it's not a Last Supper anymore. It's a wedding feast. It's a German wedding feast." So it was trying to maintain, the Italian Inquisition, intellectual purity, but without having to use the sword. So he goes quietly, even though he says at the end of the 1616 trial, he's heard to say, sort of in an aside, out of the side of his mouth, "Eppur si muove," and yet it moves, in the famous phrase of Galileo. And here, I've got a couple of portraits of him. The one on the upper right is by the great Tintoretto, and it's Galileo as a young man. He was already a significant player. Here he would be 38 years old, and he hasn't even gotten his hands on a telescope yet. Here's a painting of him by Sustermans in 1636, and we got to have a telescope in hand. And here is the old man in his house arrest, wearing his 17th century ankle bracelet, I suppose. Anyhow, he makes a lot of breakthroughs beyond astronomy, a lot of stuff that Newton's going to become interested in. He understood that the laws of nature were mathematical. A quote from him, "The universe is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures." His interest in theoretical physics anticipated the classical mechanics of Newton, which is where we're going next week, but he was also an imaginative experimenter and engineer. So he develops a theory of inertia, or so-called Galilean relativity. In his dialogue concerning the two chief world systems, Galileo states that the laws of motion are the same in all inertial frames. What does he mean by this? He used the example of a ship traveling at a constant velocity without rocking on a smooth sea. Any observer below the deck would not be able to tell whether the ship was moving or stationary. One of the objections to heliocentrism brought up by the Inquisition was, well, if we're moving, how come we feel like we're not moving? And he had to develop this theory of inertia. Well, when you're on a ship that's moving on the sea, you don't have the sense that you're moving. Or today we would say when you're in the airplane, you're in the same inertial frame as the plane that is moving. The plane's moving, you're moving with the plane relative to the plane. You think, in fact, where are you? You're in a seat. You are seated. You are in the same inertial plane. So, and a note that I point out here, that the concept of inertia ignores the scholastic origin or cause of motion. So the whole principle of inertia doesn't ask the scholastic question, where did the motion come from? It doesn't care. In fact, they will point out the Galileos of this period is that, and Newtons of this period, is that shy of something that has an impact on something that has been moving, it will, because of the law of inertia, keep on moving exactly the way it's moving in the direction that it's moving. He played with falling bodies by dropping, the famous image of whether he did this or not, who knows, by dropping balls of the same material but different masses from the Tower of Pisa. He demonstrated against Aristotle that their time of descent was independent of their mass, and that acceleration was due to gravity was a constant. Big breakthrough. Pendulums. I remember that the idea, this is from his biographer, Vincenzo Viviani, who was one of his assistants. I remember that the idea occurred to him that the pendulum could be adapted to clocks with weights or springs, serving in place of the usual tempo. He hoped that the very even and natural motions of the pendulum would correct all the defects in the art of clocks. And he even understood that sound frequencies could be measured by scraping. He noticed that by scraping chisels at different speeds, he linked the pitch of the sound. Sounds like chalk on a blackboard running up your spine in junior high. Huh? He linked the pitch of the sound and produced of the sound produced to the spacing of the chisel skips, a measure of frequency, which was accurate. So all these little observational things, we still are awaiting a grand theory that pulls all these observations together. And that is what we will be addressing ourselves to next week. And on our final slide, again, I've used a Dutchman, Johannes Vermeer, and the social awareness of science and its utility is all over art in this period. I mean, there are scores of pictures of sailing ships and the like, that we know, but there are multiple portraits of famous scientists. But look at these artistic tropes. Vermeer, these are not known people sitting for portraits. This is the idea sitting for its portrait. this is the astronomer as astronomer, qua astronomer sitting for his portrait. I mean, already they are social types, and it's out there. And it's a statement in this expansive, successful world culture that Holland has become, an intellectual hotbed since they're a republic, and you could publish books here without the interference of church authorities that you could never get away with in other places. The English and the French, all of the radical books published in French from this period all the way through 1789 are published in Holland. This is where you go for a free press. This is where you go for a free exchange of ideas. This is where you go to idealize the advances of science and other intellectual pursuits in the marketplace that supports them. So this is really a golden century for Holland, and it's a golden century for science, and it's a golden century for the universities like Leiden in Holland in this period, which many Englishmen would go off to study, as we see. So these were painted in the period of 1668, 1669, and of course, they have the grand Vermeer touch. Not only do you get the trope of the scientist, geographer, you get Vermeer's obsession with perfectly draping fabrics and shadows cast upon the wall and light coming through windows, as he always does. Anyhow, that's it. We got about 5 minutes. I'm going to stop the share. I'm going to remove the pin. And anybody have a question or an observation? Feel free. Clear as mud, eh? Jeff the Opera Addict, is that the same representation, but now in close-up?
No, this is really the Galileo in the Galileo opera.
Oh, okay, got it. Thank you.
Lou?
Yes.
This is Patricia. I really enjoyed the animation. And I had a question. I think it was Kepler, the second law of equal area.
Right.
Would the object that's orbiting go faster when it's on the part of its travel that's near the sun?
Yes.
I think yes.
Oh.
Which is one of the things that had to be accounted for.
Is that true?
Yeah, that Newton would get to.
I see. Okay.
Good observation. Anyhow, well, thank you all for being here. Next week, what did we call the lecture? I called it Mathematics, Natural Science, and the Mechanical Universe. Oh, we have another question.
Oh, hi, Lou. It's Jacqueline.
Hi, Jacqueline.
How active was Galileo during his house imprisonment?
Active in what sense? Publishing?
Academically,
active?
yeah, academically,
Yeah.
or
Yeah, he had to couch it. In other words, he still published stuff.
yeah, I thought he did.
But it was like an overview of the two systems, and he had to sound like an objective third party. On this side, we have people arguing the case for, so he had to present them as if these were equal choices, and
So somewhat self-censored.
somewhat censored.
Or
Yes.
within, he was given limits and he worked within those limits.
Right. You can't go out there and say X because we've got our eye on you, but you can go right up to the limit. And remember, the Inquisition was an interesting thing. And on the Italian side,
Mhm.
a lot of the inquisitors probably in this period would have been Jesuits.
Mhm.
These were incredibly
Mhm.
well-trained people, among whom there were people who understood that his math and his observations were correct.
Mhm.
The church has always had this kind of internal issue. This is not a bunch of wild-eyed fundamentalists
Mhm.
running around. These are sophisticated people who spoke 9 languages and what have you, who are there saying, we know that's correct. The mathematical models bear it out, and they're in effect saying, but until we manage to iron out a way of marrying this to the language in scripture for the uneducated,
Mhm.
we've got to put you on the index. We've got to put you on the index of books that are forbidden to be read. And within a couple of, as an example,
Mhm.
going back centuries, the Archbishop of Paris in the 1270s forbids Thomas Aquinas from preaching his kind of hybrid Aristotelianism.
Hmm.
Within 50 years, Thomas Aquinas is sainted by the Roman Church. But they sort of catch up to it. So it will be allowed by, I'm not sure when. I'll try to look into that.
Yeah, I was wondering how long it would take to, like you said, iron it out.
The church has always had that issue and had that kind of internal dialogue within its intellectual circles. Anyhow.
Excellent.
Okay, as Jackie Leonard used to say, ladies and germs, until next week, have a good one.